This split screen demonstrates the core conflict of temporal forecasting. On the left, we have a standard cross-sectional dataset. If an algorithm randomly shuffles the rows, the underlying patterns remain intact. On the right, we have a time series. If we scramble the time index here, the entire signal collapses into meaningless static. Standard machine learning relies on the IID assumption, the idea that every observation is independent and identically distributed. The order in which a model reads the rows simply does not matter. Time series data violates that assumption entirely. Here, observation order is critical. An observation at time t is strictly dependent on the observation at time t-1. This temporal dependence introduces specific challenges. Instead of simply worrying about overfitting, forecasters must isolate shifting temporal patterns, correct for non-stationarity, and untangle autocorrelation. If you feed time index data directly into a standard random forest or neural network, the algorithm treats every observation as an independent event. It discards the sequential logic entirely, resulting in catastrophic failure in production. To model time accurately, we pull it apart using additive decomposition. This expresses a single time series as the combination of 4 structured components. First is the trend, which captures the long-run movement in the mean level over years or decades. Below that is the seasonal component, capturing periodic fluctuations that occur at fixed frequencies, like weekly sales cycles or annual energy usage. Third is the cyclical component, representing irregular oscillations, like the business cycle. Finally, we have the residual component, the unpredictable, chaotic noise left over once the structured patterns are removed. Before building a complex model to predict these components, you need a reality check. You must establish a mathematical baseline. For data with strong periodicity, we use the seasonal naive baseline. This logic dictates that your forecast for a future date simply equals the exact observed value from the same period in the previous cycle. We evaluate predictive models against this baseline using mean absolute scaled error, or MACE. It calculates the ratio of your model's absolute error against the error of the naive baseline. If you spend months building a deep learning architecture and its MACE score is greater than 1, your model is performing worse than doing nothing at all. For decades, the standard approach was the Box-Jenkins methodology, most notably the ARIMA model. It treats each series as an isolated local mathematical environment. This maps the AR in ARIMA, autoregressive memory. The model expresses the current value as a combination of its own past values. The MA represents moving average memory. Instead of past values, it factors in past forecast errors to adapt to unexpected shocks. These mechanics require a strict mathematical foundation to function. The data must exhibit covariance stationarity. A stationary series maintains a constant mean, a constant variance, and an autocovariance that depends strictly on the lag distance between points, not on time. This graph illustrates the danger of ignoring stationarity. We have 2 independent trending random walks. When plotted together, the regression shows a tight correlation. The high R-squared is completely meaningless. Because both are non-stationary, the math generates a false positive, spurious regression. We detect this using the augmented Dickey-Fuller test. If the test confirms a unit root, we apply a transformation called first differencing. By subtracting the previous observation from the current one, differencing flattens the non-stationary trends into white noise, dissolving the false correlation. Failing to enforce stationarity guarantees spurious results. A classical model built on non-stationary data will output highly confident, entirely false predictions. ARIMA is limited by its local nature. You have to fit a completely distinct equation for every individual time series you want to predict. The operational ceiling of local modeling was exposed during the Macrodakis M5 forecasting competition, which benchmarked algorithms against Walmart's historical daily retail data. The dataset didn't require a single forecast. It required predicting 42,840 distinct, hierarchically related item sequences simultaneously. Computing, checking diagnostics, and tuning 42,000 completely separate statistical equations every single week is mathematically fragile and operationally impossible. Solving the scale problem requires transitioning from local equations to global machine learning pipelines, typically using gradient-boosted trees like LightGBM. We treat forecasting as a supervised learning problem by engineering features from the time index using a sliding window over the sequential data. First, we extract lag features. The moving window stamps past values into new columns, hard-coding autocorrelation. Next, we extract rolling window statistics. The system computes the averages and standard deviations of the data points contained within the moving frame. These rolling metrics provide localized context, allowing the algorithm to quantify momentum and volatility. We repeat this feature engineering across all 42,000 sequences, stacking every generated matrix into one unified monolithic tabular dataset to feed a central global model. Training on all data simultaneously, a global model learns cross-variable dynamics, borrowing statistical strength from related series to improve predictions for items with sparse histories. The powerful pairing of engineered temporal matrices with light GBM's raw processing efficiency is what currently dominates large-scale enterprise forecasting. A global machine learning pipeline is powerful, but it requires strict validation rules. If you evaluate it like standard tabular data, it will fail when deployed. This is standard k-fold cross-validation. It randomly assigns data to train the model, holding out one testing block. Applied to a time series, this causes chronological data leakage. The model trains on future observations, blocks 3, 4, and 5, to predict the past. This invalidates your accuracy metrics. The model has access to statistical distributions that wouldn't exist yet at the time the prediction is supposed to be made. The mandatory method is walk-forward validation. We establish an initial training block, validating on the window immediately following it. The training set expands, and the validation window slides forward. This enforces temporal logic, guaranteeing no future data bleeds into the historical training block. Without walk-forward validation, a low error rate on a validation set isn't proof of predictive power. It is merely an illusion of overfitting. Beyond gradient boosting, the modern frontier for solving complex, long-horizon forecasting problems lies in deep learning. Architectures like the temporal fusion transformer combine the sequential modeling of LSTMs with the pattern recognition of multi-head attention. Instead of relying on manually engineered lag features, the transformer's attention mechanism dynamically learns which exact historical periods matter most for a given forecast. Look at this output. Advanced models are designed to generate predictive quantiles. Instead of providing a single deterministic point forecast, they output precise uncertainty bands to quantify risk. Whether you deploy a localized ARIMA equation, a global light GBM matrix, or a deep learning transformer, the mathematical laws govern them all. You must respect chronological order, must benchmark against a naive baseline, and you must eliminate data leakage.